There we go. I was
Yeah,
muted. All right.
you're good.
So I was going to talk about humidification and design and best practices. So these slides are part of an ASHRAE talk. So there's not a lot of branding, and so there's a lot of hopefully good information in here, and not just really products. And so really wanted to talk about critical applications and design considerations for humidification in general. So I've got a stock photo of a MRI room, which is a pretty critical application for humidification, and one that comes with a lot of hurdles to overcome, particularly in controls. We can talk about that kind of stuff. If you have any questions, like Tracy said, you can submit them online, and we'll get to them. And hopefully, I'll have some time at the end, and we can just have a little Q&A period. So just want to talk about humidification in general, some critical space or space examples and challenges, and then go over different types of humidifiers and what's their best fit. We'll talk about load calc, space preparation, steam distribution, sort of pros and cons about different methods, and how to what to look out for when selecting a distribution manifold for steam. Talk about controlling humidifiers a little bit, and then a little bit about water treatment. Depending on where you are in the country, water quality can be very challenging. So water treatment does become a big advantage to have when using humidifiers. Okay, so why do we humidify? There's the growing application of indoor air quality. So a lot of that has to do with beyond hospitals now. So we're looking at schools, just for overall wellness. So there's kind of a big push for that more recently. But traditionally, indoor air quality did focus a lot on healthcare environments, hospitals, or a key component of that. And hospitals and ORs. Process applications, so that's another common application. So anything that where equipment requires humidity control, mass spectrometers or gas chromatographs may require it. So anything ranging from pharmaceuticals to university labs or private laboratories. And then more industrial operations like paint spray booths for things like auto parts or electronics, like the paint that you put on your that goes on the iPhone or the Android phone as a special gloss, can only be applied in certain conditions. Otherwise, it won't adhere to the plastics correctly or the metals correctly, stuff like that. Or in really large scale applications like painting an airplane. Humidification is critical in that process as well. For going beyond specific processes, there's maintaining integrity of materials. This would be like museums, art museums, any kind of archives. So we have humidifiers in presidential museums, the Truman Museum or Presidential Library, excuse me. So they need humidity to maintain integrity of materials. A good example, I was recently in in Utah. There's the Mormon church, or the Church of Latter-day Saints, maintains a archive for all of their like precious materials or paintings or artwork, and then records. And they've built it in the side of a mountain. It's called the Granite City Vaults, and they need humidification in there, even though it's a small load, because you don't have a lot of air exchange. You still require humidification to maintain the integrity of all the materials and the data centers that they've put in there. So it ranges from that to things where you may have more air changes, Another example would be at the Denver Art Museum, this is where I live. They have we had a Monet exhibit with hundreds of Monet paintings, and that required a whole revamping of the humidification system in a wing of the museum because the artwork was just so valuable. So maintaining that integrity really was part of the reason why they could bring that artwork out here to dry Denver. And then the growing application is, and this is growing every day, is like data centers. So any kind of small, crack units, all the way up to large industrial sized data centers that are operated by the likes of Microsoft or Facebook, or excuse me, Meta, require humidification to maintain the equipment. And they do this on different levels. So there could be, not a lot of air exchange, not a lot of ventilation, because it's mainly just computers and very few people. Or in some applications, they use a lot of ventilation, and then put the equipment in an environment where they can take advantage of free cooling from using adiabatic media. An example for the latter would be mining for things like Bitcoin or Ethereum. So that cryptocurrency mining, using free cooling because it's it's more efficient and your return on investment is larger. Going back to comfort and health, indoor air quality, this is the Sterling plot, and it shows, it's commonly seen in ASHRAE documentation, and it shows the optimum range where we keep indoor relative humidity for comfort or indoor air quality applications. And it shows why that is, because you sort of mitigate common allergens or viruses and potential for respiratory infections at that range of about 30 to 60% RH. And there's been a lot of work, and I know you've heard it before, about mitigating the transmission of viral diseases, especially coronavirus. So there's sort of two ways that this works, that humidification helps here. And this goes for COVID, it goes for the flu, the cold, and it's basically with an indoor space that's humidified and not very dry, you reduce the transmission rate of the virus, so the virus doesn't float around as much in the air. It sticks to other molecules and sinks down. And there's a bit of research on that, but then the larger part of that is that you improve the health of your respiratory system. So you're not in a stressed state, not your respiratory system isn't dry. It's healthy, and you can fight off infection much better when you're in a humidified environment, especially in places like offices, schools, airports, public places where you're spending a lot of time, and there's a lot of people. And there's a movement to 40 to 60 RH has a list of papers, 40 to 60rh.com, and a lot of material on this subject if you want to explore further. And so with different kinds of applications, where are we designing to? What relative humidity are we sticking to? And really the range sits on about a default of 40%. It's what our selection software sits at, 40%, maybe up to 50%. But really, this is what your building envelope can handle, as far as unless you really take a lot of precautions to eliminate condensation on surfaces. It's what can be managed with humidifiers. Certain laboratories might go a little higher. Process applications might shoot a little higher, but in those applications, they're probably not worried about condensation, or they have, it's like this tobacco industry picture down in the lower right. They're not worried about surfaces getting wet. They're just spraying into the space. And so, there's critical environments. I talked about this a little bit earlier. It's kind of a repeat slide, but another one would be vivariums. Places where that's where you're going to keep a little bit of higher relative humidity. In fact, we have humidifiers in. This is an interesting example in Louisiana, where you wouldn't expect to see much for humidifiers. There, it's mainly for healthcare, but we do have some at a facility that studies alligators, and so when alligators reproduce, they have to have certain environmental conditions that determine the sex of the offspring, and so we help maintain that with humidifiers. So interesting, neat application. And if the design, if you can't maintain a certain relative humidity, although in Louisiana that's not usually a problem, you might have a problem outcome if you're raising alligators. So common challenges. So for any kind of space, critical space, I say critical because whenever you're putting humidifiers in, usually it means it's you're some kind of critical operation going on there, including hospitals and those kind of like operating rooms. But you have to work against tight tolerance. So this a good example here would be like a laboratory with equipment that has to maintain a certain range. For example, anything where you're weighing like small amounts of material, if that material gets dry or adds more moisture from the air, your weights could, like in talking in micrograms, could vary and throw off your calibration on your instruments, that kind of stuff. So tight tolerances, and that is a challenge because you're bringing in outdoor air. Your humidifiers are running. Any downtime in the humidifier could mean that you may not make set point. If you have applications with a lot of ventilation, so you're required to have a lot of air changes, then that's a huge challenge because the humidifier needs to be producing steam all the time, and you're usually going to have a high capacity or high load. For example, we've been to a site where it's a laboratory, pharmaceutical and research lab, and they're making skin. So for burn victims, and so they really require a lot of ventilation, which is it's all on makeup air units. So the whole lab does an air change every minute, and they require humidity even throughout the winter, which can be quite severe. And so with very, very limited downtime, because everything they're working on is super critical and super expensive. So we need to bring in to meet those challenges. We need to bring in things like redundancy, reverse osmosis water, just to make the humidification process as fail-safe as possible. So that'll have a higher, that plays into having higher loads than typical 20% outside air applications. Other challenges if you're humidifying a space. So what I mean is a space within a space. If it's a common air handler, but you want to humidify just one room, if it's a computer room or something, you're going to have the challenge of losing your moisture through the return air into other parts of the building, and so you're going to have to size for that accordingly. And in those cases, if it's a critical or there's a critical application, it's recommended that you really isolate the space on its own air handler. And then what I want to really go into now is it helps to know the potential limitations of each type of equipment, and what is the best fit humidifier for each type of application. And so this is our lineup of humidifiers, but I'll talk about some that we even one that we don't manufacture. So we'll mainly focus on isothermal humidifiers. That means we're making steam with electricity or gas. some kind of energy source or another source of steam, so pressurized steam. And then there's also adiabatic humidifier. So that's where we're using the ambient air to vaporize the water, and we're going to have cooling associated with that. So the issue with that is that it may not play well in your environment. If your environment's already humid, it's not going to work ideally. However, if you're generating a lot of heat through a process, those might be better because you can take advantage of that heat and then get free cooling. And for isothermal, we'll talk about here we go. For applications needing any kind of tight control, it's easier to just add steam and go with that isothermal line. So this is just how it looks on the psychrometric chart. And so with adiabatic humidification, you're often going to need some kind of preheat, and that can be more difficult to control. For any kind of, generally it's easier to just apply energy with an electric or a gas humidifier and follow that line up. So when selecting a humidifier, you want to consider also other variables like, what is your energy prices, what's your water quality. This is a big one, and it's really variable depending on where you are. So if you're in the Midwest, water quality can be pretty challenging. Places like Nebraska, Kansas, Oklahoma, Utah is another one out in the Mountain West. Depending on whether you get your water from like the mountains or if it's from groundwater. Generally, if it's from groundwater, it's going to be a little more challenging because that water is sitting in an aquifer and it's absorbing minerals, and then when you boil that water, it's going to precipitate all those minerals in the tank, and that creates a service requirement or a requirement for water treatment. Energy costs. What kind of how big is your humidification load, and what kind of efficiency do you need? Controllability, space available. So these are all considerations to think about when looking for a humidifier. And it's worth, and then not just for the generator, but also for the distribution as well, for the distribution of steam. So with electric humidifiers, these are going to be the majority of what we manufacture, just because they're so versatile and they fit most applications. So the big benefit here is you're heating water to produce steam. They're compact, easy to install. You need a drain, you need electrical hookup, and you need a water supply, and you need somewhere to put the steam. In certain areas, the cost of electricity, particularly when you get up in the higher kilowatt ranges, can be represent a bit of a higher operating cost compared to, say, gas. But the controllability is really good. So with an electric humidifier, if you have a load of 20 pounds per hour and you put in, a 30 or 40 pound per hour unit, or 50 pound per hour unit, you're still going to be okay because the turn down or the ability to modulate is really good on electric humidifiers, especially on resistive heat humidifiers, which is pictured here. The other, benefit, it's you can with that turn down, you could take a larger humidifier and basically respan the demand signal and make it a smaller humidifier without really touching any of the external controls or changing anything in your BMS. It's all very straightforward. There's two types of electric humidifiers. So there's resistive type, but that's what we make, and then there's electrode type. The electrodes are generally thought of as easier to service. We have, designed our resistive humidifiers for easy service, and I'll just go back. It's very easy to remove the tank, as you can see in the center of the. Let's see if I can get my. Yeah, right here, you can see the tank. It just pulls down on rails, and you can empty out any scale. You don't have to mess with any wiring or anything like that. And that was the main, feature of electrode type, is because it used a replaceable canister, and you'd pull the canister out, throw it away, stick on a new one, and then the unit would work. The only problem with that is that the canisters cost money. They're wasteful. Some municipalities are looking at single-use plastics. I don't think humidifiers have ever fallen into that. Into that or has been seen as a single-use plastic, but maybe in the future it will be. But it does represent an ongoing cost. The other caveats to the electrode humidifiers, and by electrode I mean that these are using they're using a current passed through the water to generate heat, is that when the current goes through the water, you require some dissolved ions in the water to be conductive. And so sometimes if you have too hard water, it's not really ideal. So you may need a softener. So you may need some water treatment just to get the humidifiers to work. And they won't work with purified water just because there's no ions in the water to conduct. And once you put the bottles in, they don't work so well. After a month or 2 months, they sort of degrade with use. And so they may not be as good at modulating, or they may not have the same capacity output that's required. So then you got to change the bottle again. But in general, they're both types can fit out for one another. So if you need to replace an electrode unit, you can put on a resistive type. Kilowatt per kilowatt, it's the same amount of steam being produced. And on electric humidifiers, generally we go to about 100 kilowatts, and that's across manufacturers, to make about 300 pounds per hour. So that's our largest is 100 kilowatts. I'd say, since I'm going to talk about gas humidifiers now, the kind of cutoff point with electric, where I'd start to consider going to a gas humidifier, is somewhere in above 100 pounds per hour. And that's when I'd say, well, I think at this point you'd want to consider a gas humidifier. They're going to be more expensive, but you're going to have a larger, a lot more capacity available. Lower energy costs, so the operating costs are going to be lower. You can do good close control if the load is close to the load of the humidifier, so or the capacity of the humidifier. And they're pretty good. They're pretty efficient, with gas. And efficiency does depend on, with electric, it depends on what's generating the electricity. With the gas, the efficiencies on the unit. The kind of caveat to a gas unit is that the turn down is not as good as an electric humidifier, and that just has to do with what's the minimum amount of gas we can use to keep the burner going. And so turn down on a single module unit is maybe somewhere between 10 and 20% of the total capacity. However, with our humidifiers, the larger you get up in size, basically what we do is take multiple heat exchangers and tie them together into a single controlled humidifier, and they can operate independently off the main controller. You get better turn down with the larger humidifiers because the turn down will be the minimum output of a single module. So up to on our largest humidifiers, you may be looking at 20 to 1 turn down theoretically. And the huge benefit also to having multiple modules is redundancy. So remember I talked about the skin laboratory that was making the skin, well, they had air change every minute. You always need to have humidifiers running. And if one module goes into a drain cycle to refresh its water supply, then you have to you want to make sure that you have the rest of your modules running. And so there's a built-in redundancy here that without having to actually buy two sets of humidifiers, if you have a higher capacity, you do get that. Steam to steam, if you do have a boiler, the benefit of steam to steam is you can have a boiler. The boiler can be maintained with boiler chemicals. You're not going to put it into your air. You can put just tap water and make clean steam that goes into the air and humidifies that way. And you can create a closed loop with your boiler, so you're returning any condensate generated in the heat exchanger back to the boiler and minimizing the service. The service on the humidifier depends on how much scale forming minerals are in the water. But one of the big benefits to having gas or the steam to steam humidifier right here is that the heat exchangers, they're pretty robust. And so they'll flex, and they flex a lot of the scale on. And you can see on our steam to steam unit here, we have this little collection basket down in the corner. That basically is where the scale will fall, and you just pull it out and empty it and put these baskets back. With humidifier service is something that's common to all of them. And so especially to the generators. And so we've tried to make it as easy as possible. Steam to steam, the issue, I guess, is that controllability does depend somewhat on your steam supply. So, the capacity depends on your steam supply. So we can go up to about 1,600 pounds per hour. That has to be on 15 PSI steam. Otherwise, the unit can get derated with lower pressure steam. There, is a little bit of a lag on the heat exchanger, and it is a big volume of water in these units to boil. But generally, once you reach control conditions, the modulation is fairly good, but it's not going to be as good as an electric unit. If you do have boiler steam, but and it's clean steam, or you have no problem putting the steam into the space, a direct steam humidifier is a great way to do that. And there's two major types here. On the left, we have a jacketed humidifier, and on the right, we have an atmospheric steam humidifier. And so the jacketed, what that's doing is you have several different or two different control valves. And there's traps, temperature sensors, and a controller in the green. And the control valves are supplying steam to the airstream, but they're also supplying steam to these jackets. So this top control valve supplies pressurized steam that into a jacket that surrounds these tubes. And what that does is make sure everything's very hot. And so when you get that jacket up to over 212 degrees Fahrenheit, that's when you're allowed to open up the steam control valve for the space. And then it comes out of these nozzles without any condensate. You don't generate any condensate in the distribution. And you get really good short absorption distance with these jacketed systems. The other approach is to use one control valve and put steam into a header where the pressure is reduced to atmosphere, and then that steam will then come out of these nozzles just like as though you're producing it from a steam generator. And a benefit to this style is that you can have insulated grids. You're going to have less heat gain in the duct. So if you're putting this in an air handler, that might be beneficial. The other benefit is you only have one control valve in the space, so it takes up a little bit less space. Both of these systems can be hooked up with a condensate return that can be done on the steam pressure. So if you want to return condensate under pressure back to the boiler, that is possible. The big benefit of the direct steam humidifiers are that they can go up to pretty high capacities. So we're talking over 1,000 pounds per hour. They don't really require service. There's no scale that's going to build up that you have to clean out. All the service is put onto the boiler. So that's a huge benefit, especially if you have multiple humidifiers. Let's say you have a set of these on different ORs in a hospital. Then you're just really worrying about accessing the boiler for service and not looking in the ceiling above the operating room, which cuts down on number of operations that they can do. And for getting into that space, you need all sorts of protective gear and to suit up, and it can be a pain. So you'd rather have something that you don't want to touch in that kind of space. I will say on sizing direct steam humidifiers, it's important to consider the capacity and then the valve size. So if here's an example valve capacity table with different PSI. So we're going up to 15 PSI. If you had a capacity of, let's say, 500 pounds per hour, and you were at 15 PSI, you'd be right about here on the valve chart. So you'd use a 1-inch valve with a CV of 14. However, when that valve is fully open at 15 PSI, you're making 827 pounds per hour. So if this is an air handler, or if it's a ducted application, and it's any one of these type of if your load is just over the threshold of one of the valve sizes, when you open that valve, it's going to supply way too much steam over what you really need. So the benefit, so that could be an issue. However, with our controller, what we do is we modulate the opening of the supply or the control valve, and we dial back the span of the valve and make sure that we're not opening it to 100%. If your load is somewhere in between, somewhere lower than the total capacity of the valve. And this can be an issue when no controller is used and you put a humidistat or put a demand signal right on the actuator. So if I go back, right on this actuator, you put a 0 to 10 volt signal, and you get 100% demand, which isn't uncommon for a humidistat. If it's below, let's say it's below 5% RH below your set point, you're going to go up to 100% demand, and then all of a sudden you're saturating your duct, or you're supplying too much steam, and worse off, you're tripping the high limit. So you want to avoid that, and either use a controller strategy, or maybe change the pressure of your steam and choose a valve size that most appropriately matches your load. Going into adiabatic, a couple different types of humidifiers. This is an air and water spray. So there's not a lot of these made anymore. Everybody's pretty much moved on to a high pressure spray humidifier. And so with this, you're using water and compressed air, and this is adiabatic. So we're not generating steam. We're just blowing mist into an air handler or directly into the space. The caveat to this is noise and the energy consumption of a compressor. So that's a huge significant increase to the cost. We don't offer it. It's not really something you see often anymore. You do see ultrasonic humidifiers occasionally. They're pretty well suited to some data center crack unit applications. The benefit here is that they spray directly into the space. The caveat to them is that they require RO water. They can be expensive, and there's a bit of maintenance requirement on them. They do. You don't really have an absorption distance associated with them in the space, and they're not blowing hot steam in the space, which can be desirable for some applications. Evaporative media. This is something we've seen a lot of data centers focus in on because they're generating heat with all of the equipment, and this can be a solution, and it can be either ducted or like a fan-based solution. So you can have a fan model that's basically like a swamp cooler in the space. I've seen a lot of these go in places like in the Southwest, where you can have free cooling in the space in either a ducted or a fan-assisted model. You're not going to get really close control. You're not going to be able to. You're because the media is wet and you're waiting for it to dry. You're going to get a bit of a lag between on your controllability so it's not really fit for purpose for a tight control application, but to supply a base amount of humidity for a building space, it works really well. And you're talking about energy usage that's below a kilowatt for the just for using the pump, or the energy usage of the fan that you're using to drive the airflow. And then also on adiabatic, you have the high pressure atomizing humidifiers. So these are really good in space. I'd say are the best application where you have a large air mass that can absorb the little moisture droplets that it's generating. Ducted a little bit harder, but still possible. You can use a droplet separator that's pictured in the lower half, and you might need some preheat. So you might have a heating coil before that, and then you're going to have a cooling that's done after. And this can all be calculated in our selection software to determine the preheat required to maintain a certain RH. This can also be sized up just for cooling as well. The big benefit here is there's not much service. It's going to be basically on the pump. You do need RO water. It says preferred. It's required, because the nozzles are going to precipitate calcium, and what'll happen there is you'll clog them, or you spray dust in the space. So when you consider your design conditions, this is just to calculate load. You want to know what your design conditions are in the space, and then really you can calculate your load using the volume of the space. You can use your airflow and percent outside air. That's most common. You can also, if you have an economizer, it's definitely important we have an economizer calculation in our software. But it's important to consider in places that are very dry. The economizer might be pulling in 55-degree air outside, but it may be 10% relative humidity, and that's not going to be economical for the humidifiers running. And it may be important to limit the amount of outside air to, let's say, 30 or 40% in that scenario, because otherwise you'll have to have just so much humidification, and if it's electric, it can be rather costly to supply. It's also important to think about your distribution, and that's really what I'll focus on now, as absorption distance, airflow, whether you want a self-contained unit, and you're always going to have a load calc software. So this is what we have. And it's available to the engineering community. You just have to work through our local local rep. So talk to Holden and Associates. And this is an example of doing a load calculation. So we have 70 degrees and 40% is our internal condition or our design condition. And we have 10,000 CFM of 100% outside air. So our load is 266 pounds per hour approximately. Selected a humidifier. We do want to pay attention here because if we look at our grid size, this is in our dispersion. We want to look at several things here. We want to look at absorption distance, which you can see is right here. But we also want to look at condensate loss. Here's a pressure drop. You can look at the number of tubes. As we put in more tubes to distribute the steam, our absorption distance decreases, but our condensate loss goes up. If I back up and look at the calculated load, it's 266 pounds per hour, but our selected a humidifier, but our condensate loss can push us over the capacity of that humidifier. So we'd want to either add our condensate to the load or select a larger humidifier. So it's important to consider condensate losses. The other option here would be to insulate our grids, and then we have lower condensate loss. So just things when looking at duct distribution. Just on space preparation, all of this is gonna, if you don't have vapor barriers, if you're humidifying a warehouse and the overhead doors are open, it's not going to work really well. You want to try and keep that moisture in as best you can. And so that's, open doors, openings under doors, moisture is all going to escape. And so a leaky space will you may not be able to reach your set point on a design day if that's the case. For a space within a space, as I mentioned, install a dedicated air handling unit so you're not losing your moisture to the rest of the building. And then for humidification, pressurize the space if possible. For dispersion, the best easiest methods is to do in space. So that's on the right. Instead of ducted application, instead of ducted dispersion, this is the most efficient. The only problem is you have a humidifier then in your room or in your laboratory. It works really well for, let's say, a computer room or maybe a laboratory where it's fairly cold and you don't have enough. You can't put the steam in the duct because there's not enough airflow, or it's too cold and you'll condense. This works well for that. But it's limited capacity. Our units go up to 90 pounds per hour for in-space distribution, and that's about where most manufacturers draw the line as well. In duct, it's out of sight. This is generally the preferred method, and we have a couple different options. So there's a multi-steam dispersion grid. This is what I'm kind of focusing in on here. And that works really well for air handler applications or ducted applications where you want to have short absorption distance. The drawback here is you're going to heat up all those tubes, and that's going to create a condensate load on your and extra load on the humidifier. Now we have these single SAM tubes that are good for small applications or for applications, let's say up to 30, 40, 50 pounds per hour. Very easy to install and very economical. With distribution, you want to consider your absorption distance, and I'll go a little bit over that in a second. Your vapor trail, which is where you want to keep any controls out of the vapor trail, such as your high limit, or if there's a smoke detector or something, just keep it out of there. Temperature rise, condensation loss, pressure drop. Here's an example. Let's see, hopefully I can turn off the volume. Oh, good, it's off already. I'm going to skip. Here we go. So I hope if you can see this well, it's basically this is a steam dispersion grid and a Perspex duct. We're opening up a control valve. We're letting steam into the airstream. and you see there's a vapor trail. Those are little moisture droplets, and they extend quite far downstream of the humidification grid. This is the area where you want to keep, like if you have a high limit for the humidifier, we usually recommend 15 feet plus downstream of the dispersion grid. This is why if you start producing steam and your vapor trail is this long, it'll trip off the high limit, and then you'll go into an on-off cycle. The way we measure absorption distance is, see, there's a mirror that we drag closer to the dispersion grid. It's on this little bicycle chain on the top. When we start getting dripping from the mirror and condensation all over the mirror, that's our absorption distance. So it's measured empirically, although we have a way to calculate it in our selection software. And it's important to try and use as much absorption distance as you have. If you have a long stretch of ductwork, it makes the dispersion grid that much more efficient. And this is why. So I have two examples where there's a non-insulated grid up top, insulated grids on the bottom. The design or the humidifier selection criteria are below. So we have a load of 240 pounds per hour. It's very similar to what I had typed up in our selection software a few slides back. If we have really short absorption distance of 6 inches on an uninsulated grid, you're producing roughly 80 pounds per hour of condensate. That's a lot. That's like 25 kilowatts or 27 or a little more kilowatts, down the drain all the time. That can push you above the capacity, of your humidifier. And it doesn't matter how little you're modulating, you're going to be losing that, that efficiency. And so if you actually use 30 inches, if you have available, then your condensate loss gets down to 16 pounds per hour. It's much more manageable, and the load and loss is manageable as well. The heat gain is also lower. I mean, if you're in, let's say, an air handler, you need to put this in, you need to keep absorption distance low, but you want to be more efficient. It pays to go with an insulating grid. These are more expensive, but the payback here can be, in this situation, would be likely within a year. In most cases, it's within 1 to 2 years, depending on the energy costs. So that's just shows you. And the other one thing to consider is a heat gain on the dispersion grid. If you have non-insulated grid and it's in an air handler, and your discharge temperature could be influenced by this. So let's say you have your grid was sized with 55-degree temperature, what the absorption distance was calculated on. If you have a large heat gain, now your humidifier is seeing 51.5-degree temperature, and it's going to extend that absorption distance. So in reality, you could have a feedback that's going to push you up into 12 inches. Just on it's always, I get this question a lot. It's always important to it's always important to keep the generator as close to the distribution as possible. I get questions on, can we run it 70 feet, 80 feet? You're going to be generating condensate all throughout the plumbing from the generator to the grid. So it pays to try and keep it as close as possible. And there's just some excerpts from our IOM on how to manage that and how to manage condensate that's formed in the distribution and in the transport of the steam. So you can put in traps, and you want to slope your distribution hose or your steam piping. And we say 15%. It's a bit excessive, but I think it's a good guideline to try and get close to that. Here's just an example that shows you how quick condensate can build up. We had just turned these humidifiers on, and this is a low point in the steam plumbing with a piece of Perspex in there. perspex in there, and you can see there's already condensate that's built up. And if this low point were, any lower, you'd start really obstructing your steam from the generator to the dispersion grid, and that's going to create back pressure. It's going to create problems. You're going to start pushing the steam out, and it's going to create a condensation, or you're going to push the actual water out into the grid, which can make a mess. So it's definitely important. This is why we say to slope the steam hose as best possible. And we give a guideline of 15%. On controls, I'd say you have a few different options. You want to have a if it's a situation where, like, it's a operating room, generally we see space sensors used and the humidity is controlled either by the BMS. So there's an option for that. We do see adjustable humidistats in places where you want to have more control in the space, and then that can either be tied to sensors and, let's say, to the return duct or the exhaust air or wall humidity sensors. You're going to always have a high limit and an airflow switch with humidifiers that are putting steam into the ductwork. That's just a safety control. We can use modulating high limits. Now, what these do is help govern the humidifier output in the case where you're approaching your high limit set point, which is typically 80% RH in the duct. And that can help in situations where the airflow parameters change, like a VAV box or something. Works really well with modulating high limits. And that's a stock standard feature for all of our humidifiers now. If you need precise control, so I just got a question on keeping relative humidity below plus or minus 2%. It's our controllers are good for plus or minus 3%, but you'd want to have a industrial controller like a Vaisala where you're measuring. That's just an example. Measuring with a controller that's much more precise and has a recorded accuracy and calibration certificate. In general, BACnet Modbus, it's great for monitoring, but I would probably not rely on them to send a control signal to the humidifier. I'd rather the control signal be like a voltage signal, like 0 to 10 volts, or even 4 to 20 milliamp. The reason is that's constant, and whereas the BACnet, if you send a signal of produce 25%, then produce 50%, you may be waiting for that signal to update and then may overshoot your set point. In the case where it's the polling hasn't completed, the next round of polling hasn't completed, especially for BACnet networks where there's a lot of equipment. Where to stick your controls? It's very difficult to control on supply air. So what will happen is if you produce steam, your duct humidity is going to go up, and you're going to hunt around for signals. So it's better to actually average that, have the space sort of get an average of what's in the space, and then use the return air or a space stat to control. Temperature control is really important. If you have a 3-degree temperature change, it's going to be, a huge. You're gonna go between 100% or off on your humidifier potentially, just because their measurements are tied together. So it's always important to control temperature as well. Kind of went over this. For critical applications where downtime is an issue, redundant humidifiers works really well. A quick example, we have a testing facility where they test outboard motors. They have 12-hour periods of operation in the test. If a humidifier goes into a drain cycle, the test is no good. So you use redundant humidifiers just in case that happens. And it's really not that much of an additional cost because it's not humidifiers or just or electric humidifiers in this case, and it's not that much of a capacity issue. But it's best just to think of that at the forefront and not have have it become an issue once they're operating. Water purification really improves how long a humidifier can be running before going into a drain cycle. So with RO water, we can drain once a day. We don't, but it does not eliminate the total need to drain. And the reason is we still get a little bit of dissolved ions. They can produce scale. They can or produce foaming in your water. The reason why RO water works, or having really good water quality can get you to longer periods of operation without draining, is that if you start off with 150 or so ppm of total dissolved solids, as you operate the humidifier, it's just going to go. You're going to concentrate those ions that much more faster, and you're going to build up to a point where you start, really scaling all the surfaces in the tank, and then you see something like this. This was a humidifier that was operated without a drain cycle for probably a few seasons at least. Still worked a little bit, but they wondered why the tank was so heavy. But an important thing is, when you maintain a humidifier, you don't have to remove all the scale. You just have to, get rid of some of the material so you don't obstruct the drain. The heat exchangers and the heating elements will usually flake off any scale off their surfaces, and shouldn't impact with the operation. Softened water is usually talked about as an approach to help reduce scale. The only problem is with softened water, we can put a lot more salts in water when we raise the temperature. It's the opposite with calcium and magnesium. That's why it precipitates scale. So there's good reasoning for that, but the only problem is we get foaming. It's an issue with surface tension, and the sodium ions in the water decrease the surface tension, and the bubbles don't pop. This is just from Spirax Sarco in a boiler. Same thing happens in a humidifier, and all that foam gets out into your ductwork. This is why we use RO water for purification and to remove dissolved ions. RO systems work really well for humidifiers, and the system itself contains several components. You have the RO system, but generally they require softened water pretreatment. Just an important consideration: we do size RO systems for our humidifiers. The tank is a very important part to consider, because we want to make sure we refill our humidifiers fast so they can keep reproducing steam. So tank sizing is crucial, and something I've seen where the RO is sized for the steam output, but the tank can't refill the humidifier, and then you go into alarms and downtime. That creates an issue. And lastly, RO water is not perfect. A little bit of chloride gets through the membranes, and even if it's 5 ppm or a little lower, once you start boiling it and you concentrate it a little bit by bringing in more water, because we're operating at 100 degrees Celsius, all stainless can corrode, even with smaller amounts of chloride. And so it's important to still do a drain cycle. We typically say once a day, just drain it out, even on RO, and start with a fresh batch of water, or do like an intermediate blowdown, just to get rid of some of that water over time. All right, I know I went over a little bit, but are there any questions? All right, I see some. I disagree, maybe not here. Okay, steam traps and control devices are notorious. Probably that's a good comment. Traps, I have seen. This is in regards to direct steam. I have seen, traps fail. On a direct steam humidifier, you do have to have traps on the atmospheric steam. If you return the condensate to the drain, and if you use an insulated dispersion grid, then you really only have to have a trap on the supply. You can just use like an F&T trap. You can just use a P trap on the condensate drain, because it's no longer under pressure. So that does minimize the number of traps used. Humidity sensors need to be recalibrated. We do have the options on our sensors to give an offset or recalibrate. Typically, it's not something we see often. If you're trying to keep really accurate control, you can calibrate our sensors, but you can, like I mentioned, the industrial controller are using like a Visala controller. They'll have a whole department that sort of handles calibration. So if it's something that needs to sit at 40% and have really high accuracy and really good precision, then that may be a way to go that route.
Okay, that looks like all the questions that we have for right now.